All right, so in this section, we are looking back at some of our old transformation rules that we've covered before, some of our common functions, what they look like, as well as doing some function operations. So first, if we are just reviewing our transformations of graphs, what happens if you take function and you add something onto the end? How does that move your graph? Up. All right, what if you subtract on the end? What happens? All right, if you add on the inside, so the difference is, like, if I say x squared plus 3, that moves up. But if I say x plus 3 squared, what does that do? Right. If you have the x squared with a minus 3 on the end, that's down. But if I do x minus 3 all squared, that moves it right. All right, what happens if you multiply by a number in front? So if I say like 2x squared. Mm-hmm. Stretch or shrink, right? If I multiply by 2, it would stretch. If I multiply by a half, it's taking your height times a half, so it gets shorter, it shrinks it. Okay, what if there is a number on the inside? So if I had like a 2x all squared, what does that do? All right. What does a negative out in front do? Mm-hmm. It's like taking all of your y's and making them negative, so it flips your graph upside down. And if there is a negative on the inside, it's like making your x's opposite, so it flips it over. Any questions about this? So let's just apply it to an example. I am going to draw one graph and then put a bunch of transformations on here. You're welcome to draw a new graph every time, but I'll see how many I can put on one graph before it gets confusing. All right, if my function is the square root of y equals the square root of x, what does that look like? Mm-hmm. If you're not sure, how did we always graph them when we didn't know for sure? Maybe a t-chart. Can you do the square roots of negative numbers? No. So if you put in 0, square root of 0 is 0. Square root of 1 is 1. Square root of 2 isn't nice. Square root of 3 isn't nice. Square root of 4 is 2. And we know it's not the negative, so it's only going this way. So here's my parent function. So the idea with transformations is you don't have to make a t-chart every time I ask you to graph these. We can just think about what happens to the graph. So if you put a minus 2 on the end, what happens? Oh, it's outside my radical lines. So we may move each of those points down 2. That's my square root of x minus 2. If the minus 2 is on the inside, what happens? So it would be taking my original, that green one, and moving every point right 2. You can keep doing them on the same graph if you want. If your graph is getting, feel like it would make more sense to you to have a new one to draw some more on, you're welcome to do that too. Still the square root graph. Alright, what happens on the negative square root of x? It's like taking the y value of these points and making it negative. So 0 would stay. 1, 1, if you make your y negative, goes to 1, negative 1. 4, 2, if you make y negative, goes to 4, negative 2. Alright, if we do 2 square root of x, what does that do? It's like taking the y values of this point and multiplying them by 2. So 0 times 2 is still 0. 1 times 2 is 2. 2 times 2 is 4. So we're changing the y's. Anything on the outside changes y and it does what you think. And the last one, square root of a negative x. Inside is x. So it's like changing the signs on the x values, so that would flip it over the y-axis. So we're moving that green one and reflecting it, so 0, 0 stays. If you take your order pair and make your x negative, it go to negative 1, 1, negative 4, 2. So we just graphed a bunch of different transformations there, just trying to refresh your memory what those transformations look like and how we apply them. Sometimes, if you remember from last year, we have to graph things that maybe aren't written with transformations, so we need to be able to rewrite them first. So let's say I asked you to use transformations to graph this function. It's an x squared, so I know it's a quadratic, but I don't really know, it's not just moving up 10 because of that 6x in there. So what we did was completing the square. All right, we want to keep this just equal to f of x. We're rewriting our function. So what we do is we group the x's together, leave yourself a little space, put that plus 10 outside your parentheses. So remember, the idea with completing perfect square is, or completing square is to create a perfect square. Like if you have x minus 1 squared, we know that goes to x squared minus 2x plus 1. If you have x plus 2 squared, that's x squared plus 4x plus 4. If you have x minus 3 squared, that's x squared minus 6x plus 9. We are trying to build something like the right-hand side so we can factor it into the left. So the pattern, remember, it's always half of this middle term squared to get the constant. So I am thinking my middle term is 6. I need half of that and square it. So 6 divided by 2 is 3, and squared would be 9. So what we do is we add 9 in here so that we create a perfect square. Now, we have to cancel that out. When we first did it, we worked with both sides of the equation. So if you added 9 to one side, you added 9 to the other. If I'm keeping it all on the same side, if I add 9, what else do I have to do to cancel that? Subtract 9. So this is equivalent to my original problem. I haven't changed it. But I rewrote it so that this would factor. multiply 9 to add to 6, that'd be 3 and 3. Remember, it's always that number after you divide it by 2. So this is x plus 3 squared plus 1. And then if I asked you to graph that, that would be easy. We know x squared is a parabola, 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. How is my parabola moving? Up 1 and every point left and up. I want you guys to try B. So complete that square. Alright, looks like we did pretty well with this. So you group your x's. You leave in minus 21 on the outside. So you take that middle term, negative 4, divide it by 2, and square it. So negative 2 squared is 4, so we add 4 here. Alright, this is the only place I saw a mistake. If you add 4 on the inside, we're working on the same side of the equation. So I have to cancel that. What's the opposite of adding 4? Subtract 4. And the only reason I did that is because they're on the same side of the equation. So then this factors into x minus 2 squared minus 25. I told you didn't have to graph, but this one would move right to down 25 if you did graph it. Is that one okay? Let's try one more. What makes this problem different? Yes, the number in front of the x squared. We have a coefficient this time. Completing the square requires this to be a 1x squared. So when we learned it and we worked with both sides of the equation, we would just divide that 2 over. However, we can't touch the y equals, so we have to do it all on one side. We're going to still group our x's together, but then instead of dividing that 2, we are going to factor it out. And that minus 1 is on the outside. So I'm only taking the 2 out of my parentheses. I put parentheses around my x terms, factor the 2 out of that. If I distribute my 2 back, I still have my original problem. I haven't changed anything. Now, to complete the square, you take your middle term, which is negative 3 halves. We divide that by 2, and we square it. If we divide that by 2, we get negative 3/4. Dividing by 2 is like multiplying by half. So then if we square, negative 3 squared is positive 9. 4 squared is 16. So that's 9 over 16. But I want you to think really carefully here. We have to cancel it, so we have to put something on the end, right? Remember, there was a times 2 in front. So if I multiply this out, we have a 2x squared minus 3x plus 9/8. It turns into a 9 over 8. So what do I need to subtract off the end? The 9/8. Because that times 2 changes my 9 over 16. Is everybody with me there? So now we can factor. My parenthesis, remember I told you you could always just look at the number before you squared it. It was a negative 3/4, so it's x minus 3/4 squared. Negative 1, that's like 8 over 8. So negative 8 over 8 minus 9 over 8 would be negative 17 over 8. So that's my function. If we were to graph it, what all is happening on this one?
Going down 17.
Uh-huh.
Vertically stretched by 2.
Mm-hmm.
Going right 34.
Right. So you would make sure if you have a problem that involves both the stretching and the up and down, just save up and down for last. So vertical stretch by 2, so it's going to get taller and skinnier. Move to the right and down. All right. Do we need more completing the square problems? I want you guys to take a second and see if you can do this one. Think about the parent function. I want the parent function and the final graph using transformations. All right, so absolute value of 0 is 0, 1, 1, 2, 2, -1, 1, -2, 2. Okay, the negative out in front, we'll flip this upside down. The +1 moves it left 1. So we're going left and flipping. Pretend I hit my point there. Make it bigger. We'll be fine. How are we doing the transformation stuff? Coming back to us? I am actually going to skip this example for now. We'll talk more trig function stuff later. We're not going to do a whole lot with the graphs of those. I want to look at these. I'm probably just barely going to start this next part, and then I might quit for today, and we'll pick up with compositions and things tomorrow. But remember our function notation. F of x is the same as y. And we can do all of our different operations, adding, subtracting, multiplying, dividing. If I ask for the domain of those, we have to think, if I want f times g, that means I'm asking you to do 1 over x times the square root of x minus 1. That just gives me the square root of x minus 1 over x. For the domain, remember we talked about that at the beginning. We have a couple issues here. We have a radical and we also have a fraction. We know that if you have a square root, what has to be true about the thing underneath? So I know x minus 1 is greater than or equal to 0, which means x is greater than or equal to 1. If I have a fraction, what do we know? The bottom, the denominator can't be 0, so x can't be 0. For my overall domain, I just have to put these two together. So if it helps you, you can think about a graph greater than or equal to 1. Looks like this. If you're greater than 1, do you have to worry about 0? No. So my domain is just everything from 1 to infinity. Everything 1 or larger. Alright, let's look at the second one. If I want f plus g, so f is the square root of x, g is the square root of 2 minus x. Are those actually like terms that we can add? No, that's as far as you would go if I told you to add those things. My domain, though, we have to take both radicals into consideration. So the first one, we have just x greater than or equal to 0. The second one, 2 minus x is greater than or equal to 0. So if I add over my x, that means 2 is greater than or equal to x, so x is less than or equal to 2. Think about this on a number line. Greater than or equal to 0 is everything bigger than 0. Less than or equal to 2 is everything smaller than 2. What's the overlap? What got shaded by both of those? 0 to 2. So only the numbers between 0 and 2 can be plugged into both radicals. So that is our domain. Why don't you guys try C? So F divided by G. That's x squared over x minus 1. I'm not asking you to do like long division or anything here. I'm just wanting you to put it as a fraction in lowest terms. Nothing cancels out, so that is my F over G. In a fraction, we know the bottom can't be 0, so x minus 1 can't be 0, so x cannot be 1. So how do we write that domain?
Or 1.
1 to infinity. All right. I am going to stop here today. Tomorrow we're going to talk more about compositions and look at some graphing things again.